Hey guys, welcome back. Hopefully got over your hunger pangs from that last video. Man, I'm still hungry. But this is kind of starting the central lesson here that we've got in terms of dealing with this whole process of stoichiometry. In the last lesson, we were taking a look at that idea of chemical reactions as a recipe, and that we had to balance that recipe out because it gave us information about ratios. In this one, we're going to take that a little bit further, and in this particular case, we're going to kind of tie that into the idea of mass, because talking about how many moles of something goes in or moles of something comes out has kind of limited usefulness to us in a laboratory situation. So it's much more practical for us, instead of dealing with single moles, to deal with grams or something along those lines. So that's what this lesson's about. So make sure that with this one we've got a little bit more math going on. So have your periodic table at the ready, have your calculator, maybe a scratch paper and a pencil. And again, make sure that as we're going along with this, that you are being kind of mentally engaged. If you just sit here and watch, that's great. It's better than not watching it. But if you actually try to work out the problems, you're going to learn so much faster, and it's going to be a lot more effective for you than if you just go through. So get yourself your snack, get yourself your materials, put your feet up, get comfy, and let's get ready to go here. So, all right. So today, yeah, I was still hungry. Told you I was still hungry. Figured we'd talk about dessert for a couple minutes. Basic idea from the last time, or the big idea from last time, was that we have recipes for chemical reactions. And these recipes tell us a variety of things. They tell us what's going in, and they tell us what's going out. So the identity of the reactants and the identity of the products. So for this particular dessert reaction up here, it's a synthesis reaction, right? We need 3 reactants. We need graham crackers, you got to have marshmallows, you got to have chocolate. Those are our 3 reactants. And our product is hopefully something called a s'more, which is melted chocolate, toasted marshmallows, squished in between a graham cracker. But there's a ratio that's involved, because literally one graham cracker square or one piece of chocolate, not enough, man. You got to have the right pieces to go along with this. Mini marshmallows, no. So with this, balance your equation out. To make a proper s'more, according to my reaction here, you need to have 2 graham cracker squares, right? You need to have 1 full-size marshmallow. That's a 2 to 1 ratio. You need to have, gotta have, 3 chocolate squares. 2 is not enough, 1 is not enough, 4, too much over the edge. So you've got to have 3 chocolate squares, and if you combine those 3 things with a little bit of fire, right, it's endothermic, you will get one delicious, tasty s'more and a giant mess. So it's important to know that when we're dealing with this, that we've got ratios. That recipe tells us how much of each. It's a 2 to 1 to 3 of the reactants, and that's going to make one product. So again, we can use any pair of these things now as a conversion. We can say that 2 cracker squares equals 1 marshmallow, or 3 chocolate squares equals 2 cracker squares equals 1 s'more. Any one of these pairs of things, we can kind of go back and forth between them. They're not truly equal, but we can use them as a conversion. So 12 inches equals a foot, well, 3 chocolate squares equals a s'more. It's kind of the same idea, kind of. When we're doing this with chemistry, again, it looks a little bit funkier. It's a lot less easy to understand what we're doing when we're dealing with chemical reactions, as opposed to s'mores or hamburgers or grilled cheese sandwiches coming next. So for this, we got to focus on those fundamentals. The balanced equation gives us the ratio. It tells us what's going in, what's going out, and how much of each is involved. So for this particular equation right here, we did this in lab. It's a little bit more vigorous version of the one that we did for the decomposition of hydrogen peroxide. So hydrogen peroxide breaks down into H2O2 and O2. This black stuff at the bottom, you'll remember, was that catalyst, the black powder that we used to kind of make this reaction happen really fast. So here's our oxygen gas, and this is also water vapor. There's steam up here as well, but most of it, the water, is going to be down at the bottom. So we could do a question like this. How much hydrogen peroxide would I need to create 10 molecules of oxygen gas? Well, there's way more than 10 molecules of oxygen gas. It's going to be a really, really small value. So for us as chemists, we don't deal with the molecular level. We deal with its big brother, the molar level. And so this is kind of the equivalent question. How much hydrogen peroxide would we need to make 10 moles of oxygen gas? Much more relevant for us, because we can see that reaction. It's enough for us to be able to deal with. Actually, 10 moles of oxygen gas is kind of a lot. But anyway, for the purposes of what we're doing, it's fine. So to do with our recipe, number 1, we need to balance our recipe. You can't just say, cracker plus, plus chocolate plus some sort of marshmallow equals a s'more. You have to say how much. So first thing first, always balance your equations. It just kind of needs to be a mantra. You have to do it. So here's our balanced equation. I've done it for you. It's 2 of these guys. 2 hydrogen peroxide molecules is going to break apart to make a nice even set. We'll have 2 water molecules produced, and 1 oxygen molecule is produced. So now we can kind of start thinking about that 1 to fraction. How do we set this up? We're starting off with 10 moles of oxygen gas, and we need to get to hydrogen peroxide. So we're given hydrogen gas. We want hydrogen peroxide, so we're going to start with oxygen gas in our top left corner of our Wunderfraction. Yeah. So here's my Wunderfraction. So I start with my 10 moles of O2, because that's what was given to me in the problem. Then here's my conversion factor. I'm trying to get rid of O2, convert out of it. So I'm going to put it on the bottom of the next step. Remember, crossing down every single time. And then I'm going to try to get to hydrogen peroxide, because that's what the question asked me about. I could have asked about water, but this one asked about H2O2, so that's what I'm going to put on the top. And then the numbers that I put inside there, these 1 and 2, comes from my balanced equation. If I take a look at my recipe over here, 2 H2O2s is going to produce 1 O2. So 2 moles of H2O2 is going to produce 1 mole of O2, and that's where those numbers come from. And now it's a simple math piece. Multiply across the top, divide by everything on the bottom. So 10 times 2 is 20. 20 moles of H2O2. Again, the math itself is not the hardest part here. It's knowing how to set up those conversion factors that's really important, and we're going to add on to this in just a second. So hopefully this part's review. Moving on. Multimole ratios like this are great. They're super useful for us. It's the central piece of every problem that you're going to do. You will always do moles to moles every single time. If you don't have a mole to mole step in there, you've done it wrong, I promise 100%. But I don't know how much 10 moles of oxygen gas is. Is that a big quantity? Is that a small quantity? Do I need to get like one of those big metal canisters, or is it like a balloon? Same thing with the amount coming out, 20 moles of H2O2. Is that in a bottle? Is that like a gallon? I don't even know how much this is. So for us, we need to kind of go one step further to convert this into units that's more useful for us, like grams. And in this case, we're almost always right now going to convert to grams rather than some sort of a volume or something like that. We'll do that later on in the year, but grams. And if we want to convert from moles to grams, this should sound familiar. Dig deep. Moles to grams, grams to moles to grams. It's called molar mass. And that's those masses from the periodic table. Remember, you add them all up and you add those masses together, and that's the mass of a mole of a substance, whether it's an element or whether it's a compound, molar mass. So that's what we're going to do. We're going to add molar mass into our calculations. So here was the problem from the previous slide. How much hydrogen peroxide do you need to create 10 moles of oxygen gas? We came up with a number, which was 20 moles of H2O2. That was, again, from the previous one. Well, how much is that? So let's do that last step. Let's convert from 20 moles to grams. And again, this is a little wonder fraction. Now we're going to start off with our 20 moles of H2O2. There it is. Moles goes on the bottom. This should be H2O2, sorry. That right there should be H2O2. And this up here should be grams of H2O2. Where'd the 34 come from? Remember, oxygen weighs 16 each, so 16 plus 16. And then you've got H2, which is 1 and 1. So that's where the 34 comes from. It's the periodic table masses all summed up. And then you multiply across. So 20 times 34.02 gives us approximately 680 grams. I'm being a little soft on sig figs here. So 680 grams of H2O2, a little bit more than one of those big bottles that we had here in class. Sorry, this should say H2O2. That's bugging me right now. I'm gonna have to go fix that. Okay, here's the steps that we just went through. So this is kind of the big picture. This is where you want to take notes. If you're taking notes on something, this is the key slide right here. So balanced chemical equations give us the multimole ratio. That's our chemical recipe. This process of using that recipe to calculate mass is called stoichiometry. Being able to figure out grams of something going in or grams of something coming out using a multimole ratio, stoichiometry, that's it. We can use any product or any reactant and go from any one to any other one. And we're going to use basically 3 steps with any time that we do these. Number 1, you have to have that balanced chemical equation because you need the correct recipe. You need the multimole ratio. Number 2, you're going to have to find molar masses to go from grams to moles or moles to grams, depending on which way we're doing. But that molar mass conversion ends up being a big part of all of these. And then number 3, you want to use the Wunder fractions. Yeah, dimensional analysis is the easiest way to make sure that you're dividing when you should divide and multiply when you should multiply. There are other methods, but this one's kind of the most, I would say, idiot-proof, but it's not. It's idiot-resistant. You'll know why. So in any case, I would suggest using the Wunder fraction to make this all come together into one piece. So here's what, all right, so sorry I had to take a quick break there. Something was massively wrong in one of my equations. I had to fix it. It was driving me nuts. So here's a last little bit of this. So we're going to go kind of work our way through one of these stoichiometry problems, and then I'll give you some chance to practice here towards the end. So here's your example. This is what stoichiometry problems sort of feel like when you read them. So you've got finely powdered aluminum and finely ground iodine. Iodine is actually a solid at room temperature. It's purple. It's kind of cool looking stuff. And these two things can combine to produce aluminum iodide, the ionic compound. It's a really violently exothermic reaction, sort of interesting. No, not one that we're going to do. And then the question is, what mass of iodine is needed to completely use up 10.0 grams of aluminum? This is sort of classic, sounds like a stoichiometry sort of problem like we're doing. So it's one of these chemical recipe problems that we're going to do our Wunder fraction conversions with it. So number 1, write and balance the equation. Always got to start there. You cannot do this without writing a balanced the equation, I guarantee you it's wrong. So here's what the equation looks like. Ta-da! So we've got aluminum metal, there's what we're starting with, and iodine. Iodine's diatomic, that's why there's I2. And it's going to synthesize aluminum iodide. Aluminum's a 3 plus, iodine's a 1 minus. That's why there's a little 3 down at the bottom. And then we had to go back and balance the equation. So because of this diatomic issue right here, and this is a 3 over here, we end up with 6 iodines on the left. This gives us 6 iodines on the right. And then to balance the aluminum out, there's a 2 there. So again, don't stress about it, but that is the balanced chemical equation for this particular reaction. So here's a recipe. 2 aluminum metals is going to react with 3 iodine molecules, and we're going to produce 2 aluminum iodide molecules at the end. Next part, we have to figure out what the key mole-to-mole ratio is. And this is a matter of looking back at the question. What am I trying to figure out? In this case, the question is asking me about the relationship between aluminum, because that's what's discussed there. Let me go put this thing on. Aluminum, because that's what's being discussed here, and what mass of iodine is needed. So those are the 2 that I need to look at. So there's other pieces in the chemical equation that are there, but we may not use them in every problem. So that's when we take a look at down this ratio that I've got here. I'm only really needing to know about the relationship between aluminum metal and iodide, solid iodine. So that's why I grabbed the 2 and the 3, because those are the ones that we need. And then the next step from this is to make sure that we're using a mole-to-mole step. Every single step, every time you do a wonder fraction like this, a stoichiometry problem, you have to go moles to moles. This is always a mole to mole ratio. It's not a mass to mass ratio, always mole to mole. So if we're given grams, that means we have to go from grams to moles, and then we're going to have to do something else at the end. So molar mass is going to come into this. So what does this look like? All right, here's our molar masses from our periodic table. I grabbed the molar mass of aluminum off of there just in case you don't have yours with you. Here's the molar mass of iodine, and again, because iodine is diatomic, I have to double it, and so that's where that 253 comes from. So if you're looking at the periodic table, like that doesn't look right. Again, it's because it's a diatomic molecule, you have to have 2 times that mass. All right, moving on. Here's our equation. How do we start setting this up? Wonder fraction time. Where do we start? Start with what you're given. And in this case, the only thing we're given is 10 grams of aluminum. So that's what's going to go in my first little part of my wonder fraction. If I was drawing this on a piece of paper, I'd draw my big long line kind of left to right across here. But this is my first step of my wonder fraction. Start with what you know. I know I have 10 grams of aluminum. Next step is to figure out I got to cross this grams down. I got to get rid of grams. And the kind of the knee-jerk reaction has to be grams to moles. So our next thing that we're going to use every single time when we start with grams is a molar mass conversion. I need to convert from grams of aluminum to moles of aluminum. And again, here's our molar mass step. So grams goes on the bottom so that grams cancels out. And then that many grams is 1 mole. That's molar mass. That's the mass from the periodic table, or if it's a compound, the masses you add up. But that's a molar mass step. Next thing we need to do, well, now we've got moles of aluminum. We need to get rid of moles of aluminum. We need to convert from aluminum to iodine. And so this is our mole to mole step that we use in our other ratio. So this is the one, that's that central piece where we're going to use our balanced chemical equation to convert from moles of one chemical to moles of the other chemical. So that's what we're trying to do here, to get from aluminum to iodine. That's the central step right there. Once we've done that, the rest of it's kind of cake. So we put the aluminum on the bottom because it was on the top in the previous step. You've got to cancel them down, and then we're converting to the chemical that we want. So kind of what we know is on the bottom and what we need is on the top. In this case, the numbers 2 and 3 come from our balanced chemical equation. That's our recipe conversion. 2 aluminums reacts with 3 iodines. So that's where that comes from. That's our mole to mole ratio. And then the last step is we could stop there, except for the fact that I probably am going to want my final quantity to be in grams as opposed to moles. If I just did it right now, our final answer would be in moles of iodine. But typically when the question asks you for what mass of iodine, that means you need to convert it to grams. So we've got one more step. Anytime you've got moles and grams, it's going to be a molar mass step. So this is kind of set up upside down from the other one because we have moles here, moles cancel out, and you convert from moles to grams. And again, that's our molar mass step. This is the basic step that we're going to do every single time we do these stoichiometry problems. When we math it out, multiply across the top 10 times 3 times 253 divided by 26.98 divided by 2. You have to divide by each number on the bottom. There's my calculated answer, 141. Yeah, sig figs still count, so our answer here should have 3 sig figs because we have 10.0 grams, 3 sig figs in our problem. So our final answer here would be 141 grams of I2 due to sig figs. So again, this basic strategy, it's going to become like a mantra, like say it like 10 times before you go to bed every day. Grams to moles, moles to moles, moles to grams. It's the same thing every single time that we do these sorts of problems. All right, moving on. Your turn to try to practice one. I'll let you hit pause. See if you can figure out. I've got a couple little prompts on there. In this one, I'm going to ask you to start with that same 10 grams of aluminum, and now I'm going to ask you to calculate how much aluminum iodide could be produced. Again, different quantity. So now we're going from aluminum here to aluminum iodide over here. So again, take a second, hit pause, grab a piece of scratch paper, and see if you can at least set it up. It's fine if you don't do the calculation, but you should at least be able to write it out on paper to kind of figure out what your steps would be, even if you don't have numbers in there. So hit pause. I'm about to move on. You ready? Here we go. So here's the next step. Start with what you're given. You're given 10 grams of aluminum, so that goes in your first step. The next step is going to be grams to moles. You need to convert to moles so that we can go from one chemical to the other. So we have to do this kind of like a pre-step. So there's our grams to moles step. It's molar mass of aluminum, same as we did in the last problem. Now we have to convert from one chemical to the other, moles to moles. If I have this much aluminum, how much aluminum iodide could I get? There's our mole to mole step. Again, aluminum goes on the bottom because it was on the top. We need it to cancel out. Aluminum iodide goes on the top because that's what we're looking for. And in this case, it's a 2-to-2 ratio. Yeah, you can write it as 1-to-1 because it's the same number, but if you want to just keep with the coefficients and not worry about it, that's fine. 2-to-2, calculator will take care of it. And then the last step is that molar mass step again. We've got moles of aluminum iodide. We need moles to go away so we can end up in grams. So moles cancels to the bottom. And then this crazy number up here is the molar mass of aluminum iodide. 3 iodides and 1 aluminum adds up from the periodic table masses to 407. Again, look on the PT to get 3 times the aluminum mass, not aluminum, 3 times the iodine mass, iodine's super heavy, and then 1 times the aluminum mass, that gives you that 407. Okay, math it out. Multiply 10 times 1 times 2 times 407, that's a big number, divided by 26.98, and then divided by 2 again. And this is what you get when you do it out. You should get 151.1, whatever else is on there. Again, we've got 3 sig figs in our problem, so there's our final answer. 151 grams of aluminum iodide could be produced from just 10 grams of aluminum. It's actually pretty amazing to think about how much you're actually making from this. Okay, so here's the check. Can you do it on your own, start to finish? Again, this is where you hit pause. I'll work this out in a second, but this is a really good quiz. If you can do this, man, then you don't even need to come to class. I didn't say that. You need to come to class tomorrow. Come to school. But if you can do this, this is the key idea of this whole chapter. Everything else is kind of fluff built on top. If you're still struggling, that's okay too. And I'll put up some more example problems. We'll be working on this. But this is where we're going. So problem is 25 grams sodium hydroxide reacting completely with carbon dioxide. There's your reaction. I gave you the reaction itself. Make sure that you balance it. How much sodium carbonate was produced. So grab a piece of scratch paper, hit pause right now, and then see if you can do it. All right, I'm back. You probably didn't leave, did you? Cheaters. All right, so here we go. Balance the equation. So there's my balanced equation. When you take a look at the whole thing, we need 2 sodium hydroxides to make sure this equation is balanced. Figure out what my mole to mole ratio is. My question's about sodium hydroxide, and it's asking about sodium carbonate. So sodium hydroxide is where I'm starting, and then sodium carbonate is where I'm ending. So here's how this looks with my wonder fractions. So I'm starting with my 25 grams of sodium hydroxide given in the problem. Next up is molar mass, right? We've got to do the grams to moles step to get to moles of sodium hydroxide so that we can do our mole to mole step next. So there's the molar mass of sodium hydroxide. Again, that comes from the periodic table. 1 sodium plus 1 oxygen plus 1 hydrogen. Middle step, always, always, always have to do the moles to moles step. And this comes from the balanced periodic table. Balanced chemical equation. 2 sodium hydroxides is going to end up producing 1 sodium carbonate. So that's where those 2 numbers came from right there. Those are our coefficients from our recipe to get converting from one reactant to one product in this case. And then the last step to go out, again, we have to do another molar mass step. We've got moles of sodium carbonate, and I want to know how many grams. So that's a molar mass step. That 106.01 comes from the periodic table masses added up. So it's 2 sodiums plus 1 carbon plus 3 oxygens gives us 106.01 grams as the molar mass. So now it's just a matter of mathing it out. Once you got this part set up, man, the final calculation is actually the least of your worries. That's why I say to do the wonder fraction, because it lets you know when do you multiply by 2, when do you divide by 2. Do you multiply by molar mass or divide by molar mass? If you set up the wonder fraction every time, it won't lead you wrong, and you'll get it right every single time. So take the minute and figure out how to do it. If you calculate this all out, by the way, multiply 25 by 106.01, and then you divide by 40.01 and divide by 2 again, you get 33.1198, whatever that is. Again, sig figs, we have, looks like 3 sig figs in our problem, 25.0 grams has 3, so our answer has to have 3, so there's our final answer, 33.1 grams of sodium carbonate. So this is the step that we're going to be doing. Grams to moles, moles to moles, moles to grams. Pretty much all of these problems have this sort of mantra to them. If you can just keep saying it, it'll really help. Okay, so what do? Our review. Pretty much that mole to mole step is the most important step. Everything we're doing either before or after that mole to mole step is just to get us to that step. That's our balanced equation. That's our recipe that we need to do. In order to get that, we have to have a balanced equation. You cannot just write the equation out and pray that it works. You have to write it and then balance it, because those coefficients are the mole to mole ratio that we need. Without those coefficients, it's going to be wrong unless you happen to have the lucky equation that's pre-balanced, right? The next thing is to use the strategy of dimensional analysis. The Wunderfractions. You've been working on this for weeks. This is why I teach you this, so that you can use this as a scaffold, a strategy to be able to kind of set up these calculations so that it'll lead you through it so that you know how to get to that right answer. You'll multiply when you're supposed to, divide when you're supposed to. It's kind of a key point. That molar mass piece is usually how we go in. So we're going to convert from grams to moles or from moles to grams at the end. But we start with the given chemical and we convert from grams to moles. Second step you're going to do is convert from moles of the given to the moles of what you want. And that's from the problem itself. So look at the wording of the problem and see what it is that you need. And then the last step is usually to convert it back into grams for that needed chemical. And again, that's a molar mass step. It just happens to be upside down. That's stoichiometry. If you can do that, man, we're in pretty good shape. All the other stuff builds on this, so make sure you focus on your fundamentals. Get this one right. It's really important for you. So there you go. This is the big step that we got. I hope you enjoyed it. Hopefully you're not as hungry. The next video, grilled cheese. So make sure you get your snacks, okay? Have a good one. I'll see you next time.